The ionosphere is a region of Earth's upper atmosphere extending from roughly 60 km to 1000 km above the surface, where solar radiation strips electrons from atoms, creating a dense layer of free electrons and ions. For radio communications, this ionized medium acts as a giant dynamic mirror. By reflecting and refracting high-frequency radio waves back to Earth, it enables skywave or skip propagation, allowing signals to travel thousands of miles over the horizon without satellites. The ionosphere is not uniform. It is divided into distinct layers based on altitude, electron density, and the time of the day. The D layer, 60 to 90 km, the lowest and densest part of the ionosphere. The D layer exists only during daylight hours. Because atmospheric density is relatively high at this altitude, ions and free electrons rapidly recombine when the sun goes down, causing the D layer to disappear completely at night. It is primarily an absorber of radio waves rather than a reflector. It heavily attenuates lower HF frequencies such as the 160 meter and 80 meter amateur bands during the day. The E layer, 90 to 150 km, lying just above the D layer, the E layer experiences moderate ionization that peaks at local noon. Like the D layer, its ionization drops significantly at night, but a weak residual layer remains. It can reflect medium frequencies and lower HF signals. It is also the home of the sporadic ES propagation, highly intense localized clouds of ionization that suddenly form in the summer months, allowing unexpected long-distance VHF, example 6 meter or magic band communications. The F layer, 150 to 500 plus kilometers. The F layer has the highest electron density and is the most critical region for long-distance global HF radio communication. Because the air is incredibly thin at this altitude, ions and electrons take a long time to recombine, allowing the layer to persist through the night. During the daytime, solar radiation splits this region into two sub-layers. F1 lower, primarily a daytime phenomenon that assists in some refraction but mostly acts as a secondary layer. It merges back into the main F layer at night. F2 layer higher, this is the primary engine for global DX, that is long distance communication. It remains highly ionized day and night and provides the highest reflection angles for radio waves. The ionosphere is completely dependent on the sun, creating distinct cyclic patterns that operators must navigate to predict signal propagation. Day versus night dynamics. Daytime, the presence of the D layer absorbs lower frequencies, making bands like 80 meter and 160 meter virtually useless for long distance during the day. Conversely, strong ionization in the F2 layer raises the maximum usable frequency MUF, opening up higher bands like 20 meter, 15 meter and 10 meter for global communication. Nighttime, the D and E layers disappear and the F1 and F2 layers merge into a single F layer. With the daylight absorber D layer gone, lower HF bands open up, allowing signals on 80 meter and 160 meter to travel vast distances via the F layer with minimal attenuation. Maximum usable frequency MUF is the highest radio frequency that can be reflected back to Earth by the ionosphere for a specific transmission path. Frequencies above the maximum usable frequency pass straight through the ionosphere into deep space. Critical frequency, that is the highest frequency that will be reflected back to Earth, when transmitted straight up vertical incidence. If a frequency is higher than critical frequency, it will escape into space unless transmitted at an angle. Performance of the ionosphere changes dramatically over the 11-year solar cycle. During solar maximum, extreme ultraviolet radiation and X-rays from solar flares intensely ionize the F2 layer. This pushes the maximum usable frequency exceptionally high, allowing even VHF and upper HF frequencies like 10 meters to bounce around the globe with remarkable efficiency. During solar minimum, these higher bands often fall quiet, forcing long-distance communications back down to lower frequencies.